My topic today is on iterative and non-iterative methods to satisfy p-delta analysis requirements. I'm Alan Adams, Chief Structural Engineer and Senior Product Manager over the RAM Structural Systems software. The topic of stability and second-order analysis is a very broad subject. It would be impossible to present an exhaustive discussion in the short time that we have, so my intent is to define what is meant by p-delta, explain some possible approaches to accounting for those effects in structural analysis, and briefly highlight some key provisions in modern building codes related to these issues. Don't expect to gain a thorough grasp of this topic merely from my brief presentation today. My intent is to provide you with some insights that will help you more quickly gain an understanding of these issues as you encounter them in the codes and specifications that you're working with. So let's start out with some quick basics. As structural engineers, we spend a lot of time dealing with issues of strength. What are the loads? What are the capacities? Are the columns, beams, and braces strong enough to carry their loads? Stiffness is another major issue of concern. Are the beams deflecting too much? Is the building drift within acceptable limits? There is another aspect of design that's related to these. Membrane structural stability is a function of both strength and stiffness, and in turn it affects both strength and stiffness. Strength, stiffness, and stability are all interrelated. Consider, for example, this simple column of length h and loaded with both a vertical and a horizontal force. Using simple statics, the vertical reaction R is equal to the applied vertical force P, and the moment is equal to the horizontal force times h. Under those loading conditions, the top of the column will display some distance, delta 1. But now we need to consider the fact that the vertical force acting through the displaced location induces an additional moment equal to that force times the magnitude of the displacement, or P times delta 1. So rather than the moment being merely V times h, it is V times h plus P times delta 1. But that additional P delta 1 moment induces additional displacements into the column, delta 2. So now the moment in the column isn't just V times h plus P times delta 1, it is V times h plus P times delta 1 plus P times delta 2. But that additional moment P times delta 2 induces more displacement, which produces more moment, which produces more displacement, and on and on. If the column is stable under the imposed loads, it will converge on a final position, delta total. Each successive increment of delta and the resulting additional moment will get smaller and smaller until it reaches its final position, and the final and actual moment in the column will be V times h plus P times delta total. On the other hand, if the column is not stable, it will not converge on a final position, but it will collapse. Each successive increment of delta gets larger and larger rather than smaller and smaller until it has collapsed. And at that point, the moment and the reaction are irrelevant, as are strength and deflection. The structure is unstable and is collapsed. With that in mind, let's turn our attention now to a discussion of first-order analysis versus second-order analysis. Take, for example, this column with only a vertical load P. According to statics, the reaction R is equal to P, and the moment M is equal to 0. There is no moment in this column. But suppose there was some effect, however small, that caused the column to sway ever so slightly. That sway, or delta, would result in a slight P delta moment that would then increase the delta, etc., resulting in a succession of P deltas and the resulting increases in the P delta moments. Just as we saw in the previous example, if the column is stable, it will converge on a final delta, on a final deformed shape. As a result, the vertical reaction R is equal to P, and the moment is P times delta, not 0 as we determined initially. So the values shown on the left are those obtained from a first-order analysis, the reactions based on the undeformed shape. The values on the right are those obtained from a second-order analysis, the reactions based on the deformed shape accounting for the stability of the structure. those are the forces for which the member should be designed. So this illustrates what we're talking about when we refer to a first-order analysis or a second-order analysis. And you can imagine from this that the failure to consider stability and the second-order effects could be dangerous. There are a number of issues related to stability and second-order effects, but today we're only going to address two of these, large p delta and small p delta. Some of the others were discussed in a webinar that I gave previously, and that can be found posted on the Bentley website. Large p delta is the effect on the structure of the vertical forces acting on the displaced structure. It's the effect that we've been discussing up till now with the example of that simple column in which the vertical load P acts on the displaced shape. This is what we call large p delta. Small p delta is the effect on a member of an axial load acting on that deflected member. Similar to our discussion on large p delta, consider a member axially loaded. If anything causes the member to bend or bow, the result is an induced moment equal to P times that small displacement. That in turn causes additional bending, which causes additional displacement. If the member is stable, the shape will converge on a final delta and the resulting P delta moment. If the member is not stable, it will collapse. So let's turn our attention now to methods that we can use to account for these effects in our structural analysis. Listed here are four possibilities. You could perform a simple first-order analysis and then amplify the resulting forces when determining the member design forces. You could include the effects directly in analysis, or you could reduce the capacity calculated for the member. And of course, you could do a combination of the above, accounting for some effects one way and some another. And the codes let you do that. They offer different alternatives and allow you to account for those in different ways. There are various methods and approaches available, but I'm only going to focus on three of the most common methods: the amplified first-order analysis, an iterative analysis, and the so-called geometric stiffness method. First, let's talk about a long-established method, a useful method developed before computers came into common use in structural analysis, when things were done by hand. In the amplified first-order analysis method, an analysis is performed, and then member design forces are amplified to account for the effects of the large and small p delta. To account for small p delta, the AISC B1 factor is an example of an amplified first-order analysis. In this approach, an amplifier B1 is calculated as a function of the load on the member, the buckling strength of the section, and the shape of the curvature caused by the end moments. The non-sway portion of the moments obtained from a first-order analysis are then amplified by this B1 factor. So you do your basic analysis, and then you amplify those results by this B1 factor. To account for large p delta, the AISC B2 factor is an example of an amplified first-order analysis. In this approach, an amplifier B2 is calculated as a function of the loads on the entire structure, the amount of deflection the story would experience for a given lateral force, and the story height. The sway portion of the moments obtained from that first-order analysis are then amplified by this B2 factor. This method is also found in ACI 318. The magnifiers and their application are given in section 6.6.4, and note the similarities of the equations on the left to the AISC B1 factor for small p delta effects, and the similarity of the equations on the right to the AISC B2 factor for the large p delta effects. The amplified force method for large p delta is also found in the Eurocode. Again, note that the amplifier given by equation 5.4 is similar to the B2 factor of AISC 360. In the Eurocode, when not performed analytically, small p delta can be handled in other ways, most notably by reducing the member allowable capacity. So the Eurocode handles the small p delta in a slightly different way. The Australian AS 4100 steel code includes this methodology Most steel and concrete codes do include this methodology as an option, as we've seen from just these few handful of examples that I've given here. A second approach is to perform an iterative second-order analysis. It's probably what most engineers think of when p-delta analysis is mentioned. In the iterative approach, a succession of analyses are performed, with each succeeding analysis starting with the deformed shape of the previous analysis. That is, the loads are applied and an initial analysis is performed. With that analysis, the structure has displaced some value, delta 1. The loads are again applied to the structure, this time with the structure displaced, delta 1, and the model is reanalyzed. With that analysis, the structure has now displaced some value, delta 1 plus delta 2. This process is repeated, iterated, until the analyses converge on a final solution, or else collapses. This method has the advantage that it can be used for any structure, not just buildings. And this is the method that STAAD, for example, uses. A third approach is the geometric stiffness method. This method was developed specifically for buildings. It's considered an approximate method, but for most buildings, the vast majority of buildings, it gives very nearly the same results as the iterative method. It was originally developed when computers were slow, and the iterative method required too much computing resources and took excessively long to complete the analysis. So it has a fairly long history of use and has a number of advantages which unfortunately we don't have time to discuss extensively today. I'll hit on a couple. This figure illustrates the geometric stiffness method, whereby modifications are made to the member stiffnesses used in the analysis, based on the loads on the structure and the stiffness of the structure. These modified stiffnesses are represented here by the term K prime. Using these reduced stiffnesses, a single analysis, rather than a succession of analyses, produces the design deflections and the member forces. Theoretically, this approach gives identical results as the iterative method, but in practice, they're not exactly the same, but they are generally very, very close. And time doesn't permit a more in-depth discussion, but a web search should bring up a more detailed information for you on this methodology. It should be noted that this method only accounts for large p delta. It doesn't account for small p delta. Small p delta must be accounted for in some other way, such as by using, for example, the B1 amplification factor. So here are three of the most common methods that are used for accounting for p delta effects. Why is consideration of p delta important? Using the RAM structural system software, I analyzed and designed this building. First, I performed the analysis without invoking the option to include a p delta analysis. And then I performed a code check. So I just did a first order analysis with no p delta analysis included, and I performed a code check. So in this picture, the members are colored according to the magnitude of the interaction equation, according to the demand capacity ratio. As you can see, there are no failing members, because if there were any, they'd show up as red. And at worst, some of the lower level members are painted orange. That indicates that their interaction value is somewhere between 0.95 and 1.0, but does not exceed 1.0. So from this view, which is based on my first order analysis, this building looks like it's in good shape. However, if I invoke the option to perform the p delta analysis, I get this error message. The program has determined that the structure is unstable. And in this case, it's due to excessive p delta effects. It's not due to some modeling error, not due to some modeling problem. It's due to excessive p delta effects. Even though we saw from the previous slide that the members are strong enough to carry the design loads, they're not stiff enough to prevent the building from collapsing due to p delta effects. In this case, the cause of the problem is the long columns at the base of the structure. They're strong enough, they have capacity enough to carry the design loads, but they exhibit excessive sway capabilities such that they're susceptible to collapse even under gravity loads alone. And to see the extent of the P-delta problem, it's helpful now to invoke the amplified first-order analysis method. I can't get it to run with the regular P-delta analysis, so instead I'm going to invoke the first-order analysis, the amplified first-order analysis method, which in this case is the B1 and B2 methods, and see what amplifiers the program calculates. So I reanalyzed the structure without the option to perform P-delta analysis, but I invoked the option to apply those B1 and B2 factors. When I did that, this is the state of the building. Many members are now seen as failing. Without considering P-delta, these members appear to be adequate, but considering P-delta, this structure is shown to be unacceptable.
Alan?
Yes.
I have one question. Maybe it is relevant at this point. The question is, would the notional load be considered in both P big delta and little delta analysis, or only in P big delta analysis?
Notional loads are actually a separate topic that also is intended to account for that. In the case of notional loads, their intent is to account for buildings that are actually built out of plumb, and so the notional loads get added as additional loads on the structure. And if you have invoked the P-delta analysis, their effects will also be amplified by the P-delta effects. So yes, those notional loads would also be amplified by the P-delta effects. And the whole issue of notional loads, many may not be familiar with that terminology. Again, in a previous webinar, I discussed notional loads in more detail, and I'll reference that at the end. You can find that recording and find more information on notional loads.
Thanks, Alan.
So let's focus on the long columns, the cause of the problem here in our structure. If I select one of those columns, in this case I'm looking at column 33 at the second level, for example, we see this design report. And what we see is that that column is overstressed by 18%, whereas without the B1 and B2 amplification factors applied, this column passed, and it didn't appear to fail. Once you include the P-delta effects, the column is actually overstressed by 18%. And even more telling, the large P-delta effects are so large that the sway moments need to be multiplied by 1.9. That is, the large P-delta effect is nearly doubling the magnitude of the design moments. Note that any value above about 1.2 should be considered excessive, and they are generally even less than that. So if you run this kind of analysis and your B1 or your B2 factors are greater than about 1.15 or 1.2, you should be concerned that the structure might be unacceptably soft.
Alan, a couple of more questions on this page. I'm gonna go over quickly. The first one is why is the column green at bottom and still red at top? I guess they're referring to the picture in the page 44, I believe, or maybe in this picture. Yeah.
Okay. So
the question is again, the column green at the top and still red, green at the bottom and still red at the top. Why?
Oh, referring to the column in the middle?
I believe so, yes.
It could be because of the way the amplification works. The column segment at the top is getting the moments that are getting cranked in by the beams, and so those moments that are getting cranked into the top of the column, they're being amplified by the B2 factor, whereas the column at the bottom, it's got smaller moments. It doesn't have as large a moments as at the top of the column. So even when you apply the B2 factor and the B1 factor into this column, that column is that portion of the column is lightly stressed. Now keep in mind that in this model, if I go back, there is a partial level in this structure. So that column in the model is actually modeled as two different pieces, but and so it's being looked at as two different pieces, even though the program recognizes that it's one continuous column in the way it treats it. It's still providing us a design with the first story piece of the column, and it's providing us with a design for the second story of that column. And so that's the reason for seeing two different colors in this particular column. It's because in the model, because of a partial story at that mid-height level, the program is providing us with the design of the two different pieces of column.
Okay, Alan, thanks.
But because the top portion is shown in red, that tells us, okay, we need to do something with this column, and it's going to be one continuous piece of the same size. So once we satisfy the top of the column, then obviously the entire column will be satisfactory. So we talked about the large P delta effects and the B2 factor doubling the size of the moments in the column. Even the small P delta is having a large impact on this particular column. For this column, the small P delta effects increase the design moments by 25%. Generally, these values are much smaller, and generally much smaller, and are often 1.0. Often you'll see the B1 factors as just being 1.0 because the small P delta effects are so small. But because of the height of this column and the stiffness of this column, even the small P delta effects are very large. So you can see from the example that P delta effects can have a significant impact on the design of the structure, and again, ignoring them can be very dangerous. So let's go now to some of the common mistakes when it comes to P delta analysis. I'm just going to go over a small handful, and so again, it's important that you understand what your software is doing and what the limitations are. It's important to consider both large and small P delta. Don't forget both of them, and don't forget either one of them. Some methods and some implementations of methods only account for large P delta. Even some iterative methods might only be accounting for large P delta. So be sure to consider both. And it's acceptable to use one method for one, say an iterative analysis for one, and to use another method for the other, say the B1, B2 amplification method for the other. Don't perform both a large P delta analysis and apply the moment magnifier, such as the B2 factor, for example. They're both intended to account for the same thing. Only do one or the other. Either perform the large P delta analysis or apply the B2 factor, but don't do both. It'll be conservative if you do both, but rather substantially conservative. Gravity columns don't resist large P delta, but they in fact actually contribute to the P delta effects. Structures aren't just composed of the frame members. There are also gravity members that rely on those frame members for lateral stability. They lean on those frame members. If your model only includes the frame members and nothing is done to account for the effects of the gravity loads on the frame members, you only get the results shown in the top figure here. You get the P delta, but only the P delta due to the loads on the frame. However, as a result of these gravity members experiencing the same drift as the frames, additional P delta moments are induced into the structure. Because these gravity members have no lateral capacity themselves, those additional P delta moments must be resisted by the frames. In effect, the gravity columns are leaning on the frames, inducing additional forces into the frames. If you're using the iterative method, your model must either include all of those columns, gravity and lateral, or else it must at least include, say, a single gravity column that's modeled to represent all of the gravity columns, with all of the gravity load on all of those gravity loads, on all of those gravity columns applied to that representative column. If you're using the geometric stiffness method or the amplified moment method, the loads used in those methods must include all of the loads on the structure, not just the loads on the lateral frames. This fourth one is somewhat controversial, but P-delta effects are often unintentionally ignored when a response spectra analysis is performed. The reason is that the response spectra analysis method is incompatible with an iterative P-delta analysis. You can't do both simultaneously. Response spectra analysis is not an iterative analysis, and so you can't be doing both a response spectra analysis and an iterative P-delta analysis simultaneously to have the results, the effects combined into the final results. As a result, the P-delta effects are often neglected. People run the response spectra analysis and don't realize they're not getting any of those P-delta effects included. To include the effects of P-delta, either use the geometric stiffness method along with the response spectra analysis, which is what RAM frame does in the RAM structural system for the large P-delta, or calculate the amplification factors and apply them to the response spectra analysis results. So those are two ways that you can account for the P-delta effects when you're performing a response spectra analysis. Either using a method that uses the geometric stiffness method plus the P-delta analysis, or use the amplification factors and apply them to the results. So here are just a handful of the things to look out for, and again, make sure you understand what your software is doing and what it's not doing to avoid these and other mistakes. So I hope this presentation has been instructive and useful. It's been really short, and in this short time, I was only able to just touch on some of the issues regarding P-delta and their effects and their analysis. And the purpose of my presentation was to give you some things to think about, things to be aware of, some questions to start asking about your methodologies and your procedures and what your software may or may not be doing for you. Here's some useful resources that can give you more information on the topic. You can go to Bentley Communities where you can post questions. You can see questions that have been posted. You can see articles and wikis and blogs describing various technical issues of RAM structural system, of STAD, RAM concept, and other Bentley software. We regularly give webinars, including this Tech Talk, as well as hour-long webinars, so you can see what's coming in the future. We do videos on demand, the recordings of past webinars, and I've listed 4 that you might be interested in here. In particular, the first one, Fundamentals of Analysis and Design for Stability. This presentation was taken in part from that, and that webinar is a more extensive presentation of the information. So take advantage of the information that you can see here. If you have any questions or concerns, if you want to discuss these issues or anything further, feel free to contact me. And with that, I will turn the time back.
Before we begin the Q&A, we would like the participants to take a short poll. We would like to know, based on today's presentation, would you be interested in having someone contact you to discuss your project needs or schedule a demo? Thank you for everyone's responses. I will now be handing back over to Alan and Bülent for the Q&A.
Alan, we have a couple of more questions came in. I'm going to go over one by one. The first one is, does the iterative analysis consider residual yielding of rolled shapes?
I believe that probably has that question's in regard to residual stresses that
Yes.
from rolling. No, not it does not. And to account for that, you would need to apply some other methodology. What comes to mind is the direct analysis method that's outlined in AISC 360. And in the direct analysis method, the way that the residual stresses are accounted for is by applying a stiffness reduction, tau sub b. And again, I go into more detail on that in the other webinar that I presented. But those residual stresses can be accounted for by applying a stiffness reduction. In other codes and in other methodologies, those are actually accounted for by the K factors. So when you go to the nomographs and select a K factor, the K factor is accounting for, in part, for those residual stresses. And that's why when you do the direct analysis method and you apply a stiffness reduction, you don't have to use K factors, you can use a K of 1. But if you use, say, the effective length method of AISC, then you have to apply K factors, and the K factor in part accounts, or part of what the K factor is doing is accounting for those residual stresses.
Yes, Alan. I also add that like in direct analysis method, there is also other approaches to consider the residual stresses directly to be included in iterative analysis, but those kind of analysis computation very expensive.
And I'm sure that's in the way that the material is defined, or the
right.
number of properties are defined and then used in the finite element analysis.
Correct.
So certainly that would be a more robust approach to directly model those effects directly into the analysis, rather than the direct analysis methods approach is a simplification. It's, just apply a stiffness reduction that's intended to account for those effects.
Okay. I will move to the next question. The multi-story frame met stress demands. If the design also met code drift requirements, would there be a P delta instability?
There potentially could be. There could still potentially be an instability. Now that does bring up a good point. The code does require that you, for seismic loads, that you meet certain drift limitations. And although for wind there is no code limit, at least in the US code, there is by practice limits that engineers impose, and L over 500 is a common limit on wind. And so if you satisfied those drift requirements, your building will be stiffer than if you didn't have those requirements. And if the building is stiffer, then the likelihood of there being a P delta problem is reduced, but not necessarily eliminated. And in regard to that question, the example that I gave of the structure, that structure, that example I gave, it didn't pass the drift requirements. But I intentionally ignored those because I wanted to drive home the point that we can't ignore P delta effects. We can't just look at a code check and say, oh, everything is good if we've ignored P delta effects. especially those longer columns. Those might still exhibit a substantial P delta effects that would cause the structure to collapse, even if they met the requirements for
Thanks,
drift.
Alan. The next question is, how does RAM account for load on the gravity columns?
So the way the RAM structural system does its large P delta analysis is it uses the geometric stiffness method. And in the geometric stiffness method, just briefly, the geometric stiffness method requires that it takes the vertical load, and then using that vertical load, it comes up with a stiffness reduction in the members, in the structure, so that when that lateral load is applied, in a single analysis, because it's using reduced stiffnesses, the building drifts to that final, or displaces to that final displacement location. So theoretically, that's the same deflection location that you would have come to with an iterative approach on the full stiffnesses. We're going to start with the reduced stiffness, apply the single analysis, and we're going to end up the same place, theoretically. To account for the loads on the gravity columns, what the RAM structural system does is it takes all of the mass, or all of the loads, on the entire building. So in the RAM structural system, you've modeled the entire building. And so it knows all of the loads on all of the columns, gravity and lateral, and it uses all of that load in coming up with the stiffness reduction that is then applied just to the lateral frames. So now when you do the analysis on the lateral frames, they've been reduced in a way that they account for those effects of the gravity columns leaning on them. So it's accounted for in the way that the stiffness is reduced in the geometric stiffness method.
Okay, and the next question is, if P, I presume this is axial load, if P is small, can we ignore P delta analysis?
If P is small, then the small P delta effects obviously are also going to be small. I hesitate to just say, sure, ignore them. There are provisions in the various specifications, though, that do give you thresholds. And I'm hoping that one will come to mind at this point, but in various provisions there are thresholds that say whether or not you need to include P delta effects. And if you look, for example, at ASCE 7, there is a stability coefficient. And as I recall, if the stability coefficient is sufficiently small, then ASCE 7 says that you can ignore the effects of large P delta. So there are thresholds. The codes in some cases will set a threshold below which you don't need to include these effects. But I would hesitate to just give a blanket statement, yeah, if the loads are small, don't worry about it. Fortunately, the software that we use today, whether it be RAM structural system or STAD or something else, they offer the ability to do P delta analyses. And I would experiment, take some time and experiment, see, well, what happens if I do this? What happens if I do that? When does this become a problem? When do I start seeing it? And I really find the B1 and B2 factors very useful for that, because I can run an analysis and then look at those numbers and get a very good idea of what did it do to this member, or what did it do to this story, what did it do to this building. Whereas if you run a P delta analysis directly in the analysis, it's a little more hidden. How much did that add? So you have to run it twice, once without P delta and once with P delta, and that of course is also very helpful. So do some experimenting yourself and get comfortable with how much those are impacting the kind of buildings that you design.
Okay, the next question, for a pushover analysis, do we need to include P delta? I believe the answer will be yes.
I don't have a lot of personal experience with pushover analysis, so I hesitate. Because the pushover analysis is in and of itself an iterative analysis, I believe that just by the nature of the pushover analysis that the P delta effects would be accounted for automatically by the analysis. Does that seem reasonable, Belant?
I believe so. I mean, the pushover analysis, when it is used within an iterative solution method, and the P delta effects should be there included direct in the analysis.
Yeah, I believe that's the case. Like I say, I don't have a lot of personal experience with pushover analysis, so please don't take anything that I said about it as authoritative at this point. But that's my understanding.
Another question is, can you ignore P delta effects if your structure has a height less than X amount of feet? I guess this is again related to where we use the P delta or not.
Right. That the height of the building is not the issue. It's the stability of the members, and so height of building is not one of the thresholds that I've seen codes address. It's a matter of what the stiffness and the loads and the strength are.
The next question.
Yeah, let me just one comment while I'm thinking about it, kind of related to these questions about can I or can I, do I need to include or can I ignore?
Sure.
Just a comment in general. Usually braced frames are much, because they're stiffer by nature, they have virtually no large P delta effects on them. And so the danger of ignoring large P delta on a braced frame is much less. I'm not saying go ahead and ignore it, but just recognize that braced frames are often much simpler. But a braced frame column will still experience the small P delta effects. And so even for a braced frame, it's really stiff, but the small P delta effects, they don't care about your braces. The small P delta effects are just a function of the column and the load on the column and the bowed shape of the column, regardless of the braces that might be around it. So small P delta effects would need to be investigated even for brace frames.
Okay, on the next question, would the amplification method with B1 and B2 doing the geometric nonlinear effect equivalently?
Nonlinear. Okay, read that again.
Yes, the question is B1, B2 method doing the geometric nonlinear effect the same way?
Okay, so the B1 and B2 factors, the amplification factors, if I understand the question correctly, it's saying, are those done the same way as, say, the geometric stiffness method? And no, they're not. They're related in a way. There's some similarities in the approach, but no, they're definitely not identical. So the iterative method, the geometric stiffness method, and the amplification factors B1 and B2, they are three very distinctly different methods whose intention is to arrive at the same solution, and very often they will arrive at very, very similar solutions. And so I'm comfortable in most cases using any of those three approaches. Some have advantages over the other. Now, if we get into in the question there was a mention of a nonlinear analysis. If we're talking about, say, geometric nonlinearities or member property nonlinearities, a nonlinear finite element analysis, at that point I wouldn't be relying on B1 and B2 factors. If I'm using a much more advanced nonlinear type of analysis, then I wouldn't be relying on B1 and B2 factors for that.
Okay. The next question, if special types of moment-resisting frames are used, such as dog-bone type, can it be represented in RAM and analyzed with the iterative method?
Okay, so RAM structural system does not use the iterative analysis method. It uses the geometric stiffness method. But if you have a dog bone moment frame system, then in the RAM structural system, you can model the dog bone. And then when you do the P delta analysis, when you perform the analysis, then the effects of P delta are included along with the effects of the dog bone. And just maybe as a matter of interest, when you tell a program that this is a dog bone system, you have the option, you can either tell the program to physically model the dog bone, break it up into short segments where the stiffness of the beam is being changed because of the effects of the dog bone. So it'll break it up into, like, I believe it's 5 segments through the dog bone. So in that analysis, the stiffness reduction of the dog bone is explicitly accounted for in the analysis. And because we're performing a P delta analysis, those moments are being, in effect, amplified, because of P delta. As an alternative, you can also say this is a dog bone, but don't go to the effort of modeling explicitly the dog bone. But at the end, you can increase, to account for the additional sway that you would get, you can just multiply your drifts by, say, 15%, which is, I believe, what's the commonly accepted approach. So you have the options. But in short, yes, the effects of P delta are included in the effects of the reduced stiffness in the dog bone. That analysis takes into account all of those effects working simultaneously.
Okay, the next question, what is the recommended approach when using RAM frame to account for both large and small P delta?
Okay, so the first thing that I would probably recognize that because RAM frame uses the geometric stiffness method, that is only accounting for large P delta. So what I would do is in RAM frame, I would select the option to perform the P delta analysis. And I would go through and I would perform the analysis, and I would first, before I even bothered looking at the small P delta, I would first make sure that my structure conforms to the requirements for drift. Because then I've made sure that my structure is sufficiently stiff. And then when it comes to member design, then I would invoke the option the RAM frame gives to include the B1 factor. I would not include the option to include the B2 factor because I had it perform a P delta analysis. So I would not include the B2 factor, but I would tell it to include the B1 factor, and then I would do my code check. And now the code check is going to include the large P delta effects through the analysis, and the small P delta effects through the B2 through the B1 factor. So that's the approach that I would use. Now, if I went in that first analysis, I've included, do my P delta analysis, and if in that very first analysis I get that error message that says it's unstable, then I would go back and turn off the P delta analysis, and I would try the analysis again without P delta. And if it successfully worked, then I would kind of do a quick check on drift and you're likely to find that you need to stiffen up your members, and I would stiffen up the members to meet the requirements of drift, at least preliminarily. Then I would go back and I would invoke the large P-delta analysis, do the analysis with P-delta, which presumably now would run because we've stiffened up our structure to avoid the stability problem. And then I would check to make sure that it met the requirements of drift now that P-delta is included. And then, like I said, then I would go into the code check and tell it to include the B1 factor in the design of the members.
Okay, thanks, Alan. The next one, can you discuss gravity and mass load scale factors in the general criteria tab of RAM frame?
Okay, so again, specific to RAM frame, you have two options. You can either tell the program to use the masses that have been modeled in your model, or to use factored loads on the loads that you've modeled in your structure. And just a little bit of background for those that may not be familiar with the RAM structural system. As you're modeling your loads, you identify dead load and live load, and construction dead load, construction live load, partition load, and then you also identify the mass value. And the mass number is usually the same or close to the same as your dead load number. It may or may not include a portion of your live load. So when you're creating your model, you specify your loads and your mass, and you assign them out onto your floors and assign them to your structure. And when you get into RAM frame now knows all of the loads that you've applied to the structure. It also knows all of the mass that you've assigned to the structure. So when it comes to P delta, you're now given a choice to base this geometric stiffness calculation, this stiffness reduction. Is it going to be based on the mass numbers that you input? Is it going to be based on the dead and live loads that you input? And in earlier versions of the program, we didn't offer you the option. We just always used the mass. And we told you we'll use some scale factor on the mass to account for the fact that it may need to include some live load that you didn't include, or it needs to include load factors or whatever. And then subsequent to that, we added the option to include the gravity loads, and that's my preferred method. So I prefer to tell the program, okay, for the P delta calculations, for that geometric stiffness reduction calculation, use the factored gravity loads. And then I'll specify the factors on those loads that are the most likely controlling factors in the design of the members. And so to be conservative, you could put 1.2 on the dead and 1.6 on the live. And if your gravity loading is going to control your members, then that's probably what you should put. But because wind and seismic almost always control, you can often take a look and go, okay, the load combinations that include seismic and wind, for example, the load factors on those are, say, 1.2 dead, but only 0.5 live. So for my P delta analysis, I might tell it to use factors of 1.2 on my dead and 0.5 on my live, or 1.0 on live. So use your judgment there, but that's the approach that I take, and I will use those. You know, you need to use factored loads because in the design they need to have the effects of being factored. Because the alternative is when you do an iterative analysis, you should be doing your iterative analysis on factored load combinations, and your iterative analysis needs to be done on each combination. So if you have 180 combinations, which is common now with the codes that we have, you need to perform that analysis on all 180 load combinations if your analysis is iterative. So if you're using some other method, some other program, make sure you're performing your analysis on factored load combinations. The RAM structural system, because we use the geometric stiffness method, we actually can perform the analysis on individual load cases and then combine them after the analysis. But in order for that to be valid, you need to be using factored loads in that computation used in the geometric stiffness method. So apply factored loads of 1.2 dead plus 1.6 live or 1.0 live or 0.5 live, depending on what's likely to control in the eventual design.
Okay, Alan, thanks for all these answers. And we almost come to the end of the session. And I will hand it over to our moderator to close the session. Thank you.
I want to thank everybody for your attendance. Thank you very much.